So in this one, let's talk about the topic of a linear map. So if we have a linear map, we can call it a function between two vector spaces. Let's say v2w. So if we chose, or actually, let's make it even more symmetrical looking. These are two vector spaces, v1 and v2. But this is not a problem. We want to use some vectors v1, v2, perhaps. That will be members of these vector spaces, so it won't get confused, hopefully. So when we have a linear map, it's a function mapping elements from v1 into elements of v2 like this. And it has the following properties. So if we have any two vectors, let's say any two vectors u, v inside the v1, we have f of, and then take the addition, so u plus v actually equals the same as f of u plus f of v. That's first big property of linear maps. And also, let's say these are these are vector spaces over some field, so let's say over field f, so it's general. It can be field of real numbers or some other field. So for any constancy inside the field, underlying field of these vector spaces, and for any element of the left vector space v1, we have that f of basically c times u equals c times f of u. So you can take out the constant outside the linear map function argument, and it can multiply just the vectors being the argument from the outside. So c times f of u equals f of c times u, as we see. So these two big properties here. And now a good introduction example would be, let's say linear map. We have f, so now let's do again f, but now let's make it more concrete. A linear map given by matrix. So we would have f of f going from Rn, for example, or let's make it even more general, not just real numbers, but some field that has an element vector into mapping into these arithmetic vectors on m tuples. All right. So from n tuples to m tuples given by some matrix. So then f of some let's say vector v basically equal a v. So this is a good example. We can now take any matrix that is compatible with this. So what matrix takes in n's and m? Well, it's a matrix n by m. That means when we look at the matrix, it has n columns and m rows. So it takes in these variables, this amount of it takes in a variable, a vector of this of an n tuple, and it outputs an m tuple because that output matches the number of rows. So with that in mind, now we can construct such a matrix. So example could be, all right, so let's make it even more concrete. So fn to fm, let's make it, well, it doesn't really matter if this is more a vertical matrix or a horizontal one, that I mean wider than taller, or less tall and a wider, less wide and taller matrix, or a less tall and a wider matrix. It doesn't really matter. But what we could do, even we can make n equal to m for simplicity, for example. But we could do a concrete choice. So let's say if both n and m equal to 2, then we have f2 mapping to f2, and it's given by some matrix. Pretty much we can choose a matrix of quite arbitrary choice. So let's do 1, 2, 3, 0, for example. So we have that matrix. So now this mapping will be given, so basically f of some vector v, where v is for from the v1 or from the field second, and actually this was we should do f2. We agreed that we choose to have f2 here, so we are mapping from f to f2 as this example. So this linear map, what it means is we multiply on the left by the matrix, the input vector from f to the second. So field basic vectors, or there are two tuples with the coefficients from the field F, whatever that field happens to be. Now, actually, we are quite concrete here. We have we see these are real numbers, and what we could do to be even more concrete here, we can actually adjust it a bit and say what we actually mean is R2 now, because let's deal with real numbers. We have a matrix that we could say that this is not necessarily the field of all real numbers. We could say it's some field of some integers modulo, for example, but let's make it the more common case, sort of. And so what we now have is this linear map defined by multiplying the vector on the left by matrix. So what this means is whatever, okay, so I will let a vector v be two components x, y. And then what it means is the linear map, what it does is it takes the matrix A, multiplies by this x, y. Or actually, let's first do it in this simple, compact way of writing, which means it will do always the same. It will do 1, 2, 3, 0 times xy. So what it does is, this is matrix multiplication, this is a 2 by 2 matrix, and this is a 2 by 1 matrix. It's compatible because this and this dimension are same. So we have x plus 2y on the first entry, and then 3x on the second entry. So what this says is that for any v inside the R2, it will give us x plus 2y for the first entry and 3x for the second entry of the resulting vector under this linear map. So this is an example of the linear map, and we can see quite easily that it works out with these matrices. For example, the initial conditions f of u plus v equals f of u plus f of b. The reason is with these matrices, let's show it quite nicely. We don't even have to use this concrete example. It works out the following way. If you have a matrix multiplied by u plus v, and no matter, not in necessarily relation to the names we've chosen so far, let's just make this a separate realization. Actually, matrices have this property with distributivity, so actually it's the same as a u plus av. Well, and thereby, if we define the whole linear map as multiplying by matrix from the left side, well, we have one and another instance of the thing that basically matches the idea of f u plus v equals f of u plus f of v. And also we do the same with scalars. So a of c times v, we know when we multiply a vector on the right to a matrix, we can take out the constant that multiplies the vector outside the whole calculation. So it would end up like this. It will work out. So these things are satisfied. Also for the zero vector, if you take a zero vector, it maps it to 0, another thing to observe with linear maps. And there are other things we can observe, or other examples, but we can leave that to another one. So this was in general introduction for initial overview of how to look at linear maps.